Hi all, let's take a look at the section 10.6, which discusses power series. You'll see here in the first problem, it's giving us a series where we have the function x raised to the n power divided by the exponential function 4 to the n. So this would be x to the first over 4 to the first plus x squared over 4 squared plus x cubed over 4 cubed, so forth. Now, our goal in these power series problems is to find the values of x that will cause the series to converge. Typically, what we do in order to do a method that will always work is we use the ratio test. And you know that the ratio test guarantees convergence if the limit as n approaches infinity of the ratio of a sub n plus 1 over a sub n is less than 1. Now, at the values where it's equal to 1, that's when the ratio test is going to be inconclusive and we'll have to test those endpoints. This first problem, that didn't even really need to be done because it's simply asking for the radius of convergence. That means the distance from the center of convergence to one of the endpoints. And that you can just find by setting x less than or equal to it. Well, I'll go ahead and talk about it as I get to it. So in this problem, we have the absolute value of a sub n plus 1 over a sub n. That's going to be x to the n plus 1 over 4 to the n plus 1. We're multiplying that by the reciprocal of a sub n, which is 4 to the n over x to the n. Now I can say the x to the n plus 1 over x to the n. It's going to simplify to give me an x in the numerator. I know I have one more factor of 4 in that denominator, so I'll have the absolute value of x over 4. Now, I know that the ratio test tells me that that's going to converge if the limit as n approaches infinity of that fraction is less than 1. Well, there's no n left in it anymore. So I know the absolute value of x over 4 has to be less than 1, which that tells me that x over 4 has to be less than 1 or greater than negative 1. And then if you solve for x, well, x has to be less than 4 or greater than negative 4. Now, when I was talking about the radius of convergence just a moment ago, I said that's the distance from the center of convergence to any endpoint. Well, if your convergence interval goes from negative 4 to 4, clearly this function has is most convergent if you just say, well, what if I just let x equal 0? Then your numerator is always 0. 0 divided by any number is 0. Of course, the summation of zeros converges. So this is definitely convergent if x is 0. But then if you move away from that center, you can go 4 up or 4 down, meaning the radius of your convergence is 4. And you'll see that that is what I had for my answer here. The radius of convergence is 4. It's just the distance from the center of convergence to either of your endpoints. Now, actually, we don't need to see that solution. We just did it. For number 2 here is my work for it. It gives us the integral of x to the n over, strangely, the 11th root of n times 2 to the n. And this time it's just asking us to determine the radius of convergence again. I was thinking that this one was interval of convergence, but it looks like, again, it's, nope. So it says radius of convergence there, but then it asks for an interval of convergence down here for your answer. So the question really should read the interval of convergence. We have a sub n plus 1 over a sub n for our ratio test here. Please notice for the a sub n plus 1, I just said, well, it's just your general term evaluated at n plus 1. Excuse me. And then instead of saying divided by a sub n, I always multiply by the reciprocal of a sub n, same thing. Now, whenever I'm simplifying this, I know that I'm going to have one additional factor of 2 in the denominator because of the 2 to the n plus 1. I'll have one additional factor of x in the numerator. That's where that came from. And then the 11th root of n over the 11th root of n plus 1 doesn't cancel until I put it inside of a limit as n approaches infinity. So you'll notice in showing my work here, I can say, well, now the ratio test wants me to take the limit as n approaches infinity of this absolute value of a sub n plus 1 over a sub n. When I do that, these square root of 11 n over the square root of 11 n plus 1, that's just a factor of 1. The 11th root of some large number over the 11th root of some large number plus 1, it's essentially the same in the numerator and denominator. That's going to have a limiting value of 1. So this is just approaching the limit as n approaches infinity of this expression is equal to the absolute value of x over 2. So then we can say, well, what do we know? We know the ratio test tells us that it has to be less than 1 in order to converge, which tells me x over 2 has to be less than 1 or greater than negative 1, getting rid of the absolute value. Multiply by 2 on each side of the inequality, and that shows me that x is somewhere between negative 2 and 2. Now, if they only wanted the radius of convergence, I would say, well, the radius of convergence is 2. But they want more in this problem. They want the interval of convergence. So that means I need to check the endpoints. I need to determine what's happening at 2 and what's happening at negative 2. In this problem, I checked what was happening at 2 first. If I allow x to equal 2, your numerator is 2 to the n, your denominator doesn't change. But now I know, hey, that's going to be very clear what happens. Those factors of 2 to the n now would cancel out, and this would just be the series of 1 over n to the 1/11th. I know exactly what happens with that because it is a divergent p-series. Please remember, the p-series converge only if the value of the exponent in the denominator is greater than 1. Anytime it's less than or equal to 1, it's a divergent p-series. That fraction's not getting small enough, quick enough in order to not diverge. So I can say that's a divergent p-series. Now, if I test when x is negative 2, so you said, well, in the place of x, I plug in a negative 2, so you're going to have a negative 2 to the n in the numerator. Please keep in mind, negative 2 to the n divided by positive 2 to the n, that's just going to be negative 2 over 2 to the n, which is a negative 1 to the n. So I'd have negative 1 to the n over n to the 1/11th. And now while this looks similar to the one previous, completely different now, because the only thing I need to do to this is the alternating series test. And I can say, well, the alternating series test tells me that this series converges if the limit as n approaches infinity of the non-alternating portion goes to 0. Well, it does, because I can say the limit of 1 over n to the 1/11th, that'd be 1 over infinity to the 1/11th power. Yeah, that's going to 0. Since that goes to 0, this series converges when x is negative 2. That means I can include negative 2 in my solution, but I cannot include 2 because at 2 it diverged. So my interval answer is bracket negative 2 to 2, parenthesis, and you'll see that that's exactly what I entered in to achieve. For the next question on achieve, this was probably the longest one in this section because it had 3 parts to it. No problem. Let's take a look at the first part. It gave me the summation of the function 5x raised to the n power divided by 12 to the n power. So I said, okay, ratio test. A sub n plus 1, that's going to be 5x raised to the n plus 1 power, divided by the denominator, 12 to the n plus 1 power. Divide by a sub n, multiply by its reciprocal, 12 to the n over 5x to the n. I can clearly see here that that's going to simplify to be 1 factor of 5x in the numerator, and you have 12 to the first power in the denominator. Please keep in mind, all the n's canceled out. So when I take the limit as n approaches infinity, it doesn't do anything. You just say, well, you've got an absolute value of 5x over 12. Now, what the ratio test tells you is that the limit as n approaches infinity of this expression needs to be less than 1. Okay, then that means 5x is going to have to be, I could multiply by 12. 5x is going to have to be less than 12 or greater than negative 12. Now we can divide by 5 in all 3 portions and get, okay, x is some number between negative 12/5 and 12/5. If it is, we are guaranteed that that series will converge. If it's not, In other words, if it's equal to one of the endpoints, we don't know. So I have to test the endpoints. I tested 12 over 5 here. When I put a 12 over 5, please keep in mind, you're just replacing x with a 12 over 5. Well, 12 over 5 times 5 is going to give you a 12 to the n power up there. That's where that came from. 12 to the n over 12 to the n is just 1. Now, this would confuse a lot of people. It shouldn't. Think about that. Your series is 1 plus 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 1 forever and ever and ever. Clearly, that's not going to clearly that's not going to converge. It's going to diverge off to infinity. Now, if you wanted to use a formal test, you could say, since the limit of the general term does not equal 0, this diverges due to the divergence test. The limit as n approaches infinity of the general term would have to go to 0. Since it doesn't, diverges. Now, similarly, if I plug in a negative 12 over 5 for my x term here, you would have 5 times a negative 12 over 5. It's going to be a negative 12 to the n in the numerator, and your denominator is 12 to the n. So now your series, instead of just 1, it's going to be negative 1 raised to the n power. So one term is going to be negative 1, then positive 1, negative 1, positive 1, negative 1, positive 1. Now you might think that that converges, but it doesn't, because in order to converge, it has to approach some specific number. The way that we can show that this diverges is you can say, well, can I take the limit of the general term and say that it's 0? No. You can say that negative 1 to the n is either going to equal a 1 or a negative 1, certainly not equal to 0, thus it diverges. And therefore, we can say the interval of convergence for this first portion is just negative 12 over 5 to 12 over 5 with both of the endpoints excluded. And you can see that's what I did there. Now this next one, the only difference is my denominator is going to have a factor of n in it. And you can see the difference in my answer already on my Achieve page is that it made me include the first endpoint. Well, let me show you the work that I did for that. So here in 3 part B, it's essentially the same problem, it's just that additional factor of n. That additional factor of n calls my function be 5x to the n plus 1 over n plus 1 times 12 to the n plus 1 times the reciprocal of a sub n, so I had my n times 12 to the n and 5x raised to the n power in the denominator. It's essentially the same problem as I had before, except the problem before simplified down to be 5x over 12. Now it's 5x over 12 times n over n plus 1. And that's specifically the way that I separated it up when I did my limit as n approaches infinity, because I can say this expression doesn't have an n in it. What happens to this expression of n as n goes to infinity? When you say anytime you have a polynomial in the numerator and a polynomial in the denominator, if the degree of the numerator and denominator is the same, which is true, then the limiting value is just the fraction of leading coefficients. Clearly, that just goes off to 1. So I have 5x over 12 times 1, which takes me back to my 5x over 12 again. And you can see, well, for that reason, I'll still have x has to be between negative 12 over 5 and 12 over 5. But I still have to check my endpoints. So this time I'm testing the negative 12 over 5 first. It's still going to give me a negative 12 to the n in the numerator. My denominator is going to be n times 12 to the n, since there's no x down there. Okay, now the negative 12 to the n over 12 to the n still reduced down to negative 1 to the n power. But unlike the previous problem, what separates it is in the previous problem, I just had that negative 1 to the n, and it diverged because it never approached 0. It's not the case now. Negative 1 to the n divided by n, we know that that converges because the alternating series test says that if you can take the limit of the non-alternating portion of this general term and show that it goes to 0, then this series converges. 1 over n, as n goes to infinity, does go to 0. That series converges by the alternating series test. So I can say, okay, I'll have to have a bracket around negative 12 over 5. What about 12 over 5? If you plug a 12 over 5 in for x, you're going to get 12 to the n in the numerator again. That 12 to the n and the 12 to the n in the denominator cancel, and that's just going to give you the series 1 over n. instead of negative 1 to the n over n, I have 1 over n. And I can say, well, I know that that's divergent because this, I don't have to use a comparison test or anything. This is a p-series with p equals 1. And you're supposed to remember the p-series test says that anytime p is less than or equal to 1, your series is going to diverge. You would need p to be greater than 1 to converge. So that means that 12 over 5 cannot be included in your interval of convergence. And you'll see here I put the interval of convergence is bracket negative 12 over 5 to 12 over 5. Now there was a third part of this problem. In the third part, the only difference is it's going to change that n to a factor of n squared in your denominator. It really doesn't change much in the workings of the problem up here. You can see where I still have to take my a sub n plus 1, divide it by a sub n. The only thing that's different from the previous two is I'm going to have an n plus 1 squared in the denominator, and I'll have an n squared in the numerator of that expression. So now when I bring that down to take my limit as n approaches infinity, just like I did in the last problem, I'm going to take the part that doesn't have a factor of n out front and then say, okay, times the fraction n squared over n plus 1 squared as n goes to infinity. I automatically know yet again, as n goes to infinity, this fraction goes to 1 because you're going to have a polynomial in the numerator and a polynomial in the denominator. The degree of both is going to be degree 2. You're going to have a 1n squared over 1n squared. As n goes to infinity, that fraction goes to 1. So I take the limit and I just get the absolute value of 5x over 12 for yet again a third time. And I can say, well, okay, then that's going to tell me that this series converges if x is between negative 12 over 5 and 12 over 5. But now I can say, well, all right, but what happens at the endpoints? When I plug in a negative 12 over 5, my numerator becomes negative 12 to the n, just like it did in the other two cases. My denominator, I'll have the n squared and the 12 to the n. Negative 12 to the n over 12 to the n reduces down to negative 1 to the n. If I divide that by n squared, that's clearly convergent. For the same reason the last one, negative 1 over n, was convergence, because of the alternating series test. You can say, can I take the limit of the non-alternating part and show that that's going to 0? Yeah, 1 over infinity goes to 0. When I plug in the 12 over 5, I get 12 to the n over 12 to the n reduces down to 1. So I get the series of 1 over n squared. What do I know about that? I know that that is a convergent p-series. So unlike the last one that was a divergent p-series because p was equal to 1, now the p in your p-series is equal to 2, and all you need is a p-value greater than 1 in order for that series to converge. So we can say this series not only converges at negative 12 over 5 now, but also at positive 12 over 5. So you have brackets around both endpoints there. So you'll see that completes this gorgeous problem here with the 3 iterations of the problem where we have to test the endpoints in each version, with that last one being the brackets around both endpoints. Okay, up next, when we look at number 4, show my work for it here. We have the series n plus 1 factorial times x to the n. So I can say, okay, a sub n plus 1 over a sub n. A sub n plus 1 says just plug an n plus 1 in the place of n in your problem. Well, then that's going to become n plus 1 plus 8, which is n plus 9 factorial. Then you're going to have times x to the n plus 1. So this is a sub n plus 1 divided by a sub n. Well, a sub n is right here, n plus 8 factorial times x to the n. This becomes really easy because I can say, well, n plus 9 factorial is n plus 9 times n plus 8 factorial. So that n plus 8 factorial cancels all of the n plus 9 factorial except for the factor of n plus 9 itself. Similarly, x to the n divides into x to the n plus 1 and leaves me x to the first. So now I would have to take the limit as n approaches infinity of n plus 9 times x. Now, if I let n go to infinity, clearly this goes to infinity, and your ratio test would tell you, well, it has to be less than 1 to converge. Well, that's not going to be less than 1. Now, please remember in our power series, and I'll bring back up my notes here, we always know a power series is going to converge in one of 3 ways. So there has to be some convergence. So sometimes they always converge for any x. Usually there's some specific interval of x that they converge. But in the general sense, they're going to converge at their center of convergence, which is always x minus c. It's the value of c in here. Now you might say, well, you had just an x in this problem. Well, your value of c is understood to be 0. So if you raise that x, or not if you raise it, but if you plug a 0 in the place for that x, then every single term of your series is going to be multiplied by 0 to a power, 0 to a power. So you say, well, okay, the one way that this limiting value might be able to be less than 1 is if x is 0, then every single term of your series is multiplied by an additional factor of 0, which will make it converge. So we say it diverges to infinity unless, and please remember, power series always converge at least at the center of convergence. The center of convergence for this problem, since it's not being shifted by any value of c, is x equals 0. So you can say, well, all right, x equals 0 should be my only convergence, and you'll see that's what I did here. The only value that makes this series converge is at x equals 0 itself. That wasn't too fun of a problem. I like it when we have an interval that converges, such as number 5, we have that. In number 5, we have the series x minus 8 to the n power divided by n to the 7th plus 2. All right, so what did I do? Same thing I always do, ratio test. A sub n plus 1, it's your series here evaluated at n plus 1, so you have n plus 1 to the 7th plus 2 in the denominator, times the reciprocal of a sub n, have the n's to the 7th plus 2 in the numerator, and x minus 8 to the nth in the denominator. I know when I reduce this down, I'm going to have one more factor of x minus 8 in the numerator, multiplying that n to the 7th plus 2 over the group n to the 7th, or sorry, n plus 1 to the 7th plus 2 in the denominator, and this canceled out. Now, when I take the limit of that expression as n approaches infinity, I know all I need to do is say, well, this is going to be x plus 8 times the fractional expression in terms of n. And just like I've done on several problems before, I can look at this and say, it's just going to be a polynomial in the numerator and denominator. It's going to be degree 7 in the numerator and denominator. I'll have a 1 n to the 7th in the numerator. I'll have a 1 n to the 7th in the denominator. And none of those other terms matter. This is, again, approaching a term of 1. So this is going to be x minus 8 times 1 becomes the absolute value of x minus 8. Now I know that that has to be less than 1 according to the ratio test. So I can say, all right, then that tells me x minus 8 needs to be less than 1 or greater than negative 1 when I get rid of the absolute value. Now I just add 8 to all 3 components. And you say, well, that's going to give me 7 is less than x, which has to be less than 9. So I already know that this series converges if x is any value between 7 and 9. Check the endpoints. I check 7. And I can say, well, if x is 7, please think about what I did here. This shouldn't be difficult at all. If you plug in a 7 for x, you get 7 minus 8. Well, that's a negative 1 to the n power. Your numerator becomes negative 1 to the n. Here's your denominator. What do you know about this series? Well, you can say by the alternating series test, it is alternating. Since the limit of the non-alternating part would go to 0 as n goes to infinity, converges. Now, do we need that alternating sign up there to make it converge? Absolutely not, because look, when I plug the 9 in, your numerator would just be 9 minus 8, which is 1. Do I really care if 1 is raised to the n power? No. 1 to the n is just 1. So your numerator simplifies to just be a 1. Your denominator is n to the 7th plus 2. That definitely converges. And you think, why does it converge? Now, I technically said I'm using the comparison test. I looked at it and said, oh, it converges because it's a p-series with p equals 7. Technically, it's not a p-series because you got that +2 down there with it, but that makes it converge even more. You can say it is smaller than a convergent p-series with p equals 7 because 1 over n to the 7th would be larger than 1 over n to the 7th plus 2 because this has a larger denominator, which makes the fraction smaller. So this is smaller than a convergent p-series with p equals 7. So thus, by the comparison test, this also converges. Converges at both of our endpoints. We put brackets around both and say, that's a beautiful question. For number 6 here, again, it gives me a series. This time I have a natural log in it, which keeps things a little interesting. Notice the work I did on this one. I said the series x to the 3n plus 1 divided by the natural log of n. Now, I was thinking that this one probably is not going to converge for very many values because that denominator, the natural log of n, it's a pretty small denominator. It's not getting large fast at all. So in order to determine the interval of convergence, I said, well, let's use the ratio test, a sub n plus 1. Now, I said, and I skipped a step here. Please make sure you see where this comes from. I said, if I plug an n plus 1 in for n, I would get 3 times n plus 1 plus 1. Well, that's 3n plus 3 plus 1. I just said that's x to the 3n plus 4 power there. That's plugging the n plus 1 in for n. Then in your denominator, the natural log of n plus 1 times the reciprocal of a sub n, natural log of n, over x to the 3n plus 1. Now, please be careful here. You should automatically recognize, well, you're going to have 3 more factors of x in your numerator than you are your denominator. You would subtract exponents, 3n plus 4 minus the group 3n plus 1. It's going to give you x to the 3rd power. Now, the non-x terms, I just kept as a fraction off to the side and said, well, that's going to be times the expression, the natural log of n over the natural log of n plus 1. Now I take the limit as n approaches infinity. And inside these logarithms, I know the degree of n is the same. So you'd say, well, okay, that's just the numerator and denominator is always going to be the exact same size. That's going to go off to a fraction of 1 as n goes to infinity. And I'll have x cubed times 1 becomes the absolute value of x cubed. We know that that needs to be less than 1, which tells you x needs to be less than 1 or greater than -1. You just take the cube root of both -1 and 1. Doesn't change anything. So now, here's my interval of convergence. And I can say, well, let's test the endpoints. I test a -1. What happens when you plug a -1 into this function? So my numerator would be -1. Now notice, I didn't worry about the 3n plus 1 power. The reason I didn't, it's the same thing as -1 to the n. The reason I know that, and the reason you should know that, is because think about this. If n is any even number, like 10, 3 times 10 plus 1, then your exponent is odd. -1 to an odd number is going to be negative. Well, what if n is any odd number, like 11? 3 times 11 is 33 plus 1 would be 34. So for any odd number of n, the exponent is going to be even. For any even number of n, the exponent is going to be odd. I might as well just call it -1 to the n. It doesn't matter as long as you understand this is just an alternating series. One term is going to be positive, next term negative, next term positive, next term negative. I needed to know that because I'm going to use the alternating series test. And I can say, well, let's take the limit of the non-alternating part, and that's going to be 1 over the natural log of n. And as n goes to infinity, that denominator also goes to infinity, and 1 over infinity goes to 0. Since that limit is 0, that's conclusive evidence that my series converges. Now, what about when I plug in the right-hand side, the 1? Well, when I plug in a 1, it doesn't matter what power the numerator is to. It's always just a 1. And I'd get 1 over the natural log of n. And don't be confused by that. We know it diverges. How do we know it diverges? I just thought real quickly, we know that the p-series with p equals 1 diverges, 1 over n diverges. We know that this denominator, the natural log of n, is going to be far smaller than n. So a smaller denominator makes this fraction way larger than this fraction. So what does it mean if you're larger than a series that diverges? Well, you're a series that diverges. So conclusively, this would diverge by the comparison theorem with the harmonic series of P series P equals 1. So we can say we cannot include 1, but we do include the negative 1. So bracket -1 to 1, and you'll see that was the answer on achieve. For my next question on here, number 7, and this section is depressingly short. Let's see. We have the series 27 to the n times x minus 6 to the 3n plus 2 power. Okay, so what I did here, what you should always do, you should use the ratio test to start off your problem. So I said, let's think about what happens to a sub n plus 1 over a sub n. A sub n plus 1 becomes 27 to the n plus 1 times x minus 6, and this would be 3n plus 3 plus 2, called it the 3n plus 5 power. Now you're dividing that by a sub n, 27 to the n, x minus 6, 3n plus 2 power. So now I can say, well, clearly I'm going to have an additional factor of 27 in the numerator and 3 powers on the group x minus 6. So I'll now say, well, I need to take the limit as n approaches infinity of that expression, and clearly there's no n left in it. It all canceled out. So you just say, well, doesn't matter if n goes to infinity, your expression is still going to be the absolute value of 27 times x minus 6 quantity cubed. That needs to be less than 1. So I just said, well, then that means that this expression needs to be less than 1 or greater than -1. I went ahead and divided by 27 on all 3 parts of that inequality to get -1/27 less than x minus 6 cubed less than 1/27. Now, I took the cube root of all 3 parts of our inequality, gave me -1/3 is less than x minus 6, which is less than a +1/3. Now, I had to add 6, so I just thought of it in my head as adding 18 over 3. Add 18 over 3 here, you get 17 over 3. Add 18 over 3 here, you get 19 over 3. So I am 100% sure this series is going to converge as long as x is between 17/3 and 19/3. But I don't know what happens at the endpoints because the ratio test doesn't tell us that. So I plug in the left-hand endpoint, 17 over 3. When I do, I'll get 17 over 3 minus 18 over 3 inside there. That's going to be a -1/3. So you'll see that's why I have 27 to the n times a -1/3 to the 3n plus 2 power. Now, I needed to try to get these to where I could get one nice common ratio to a power. So here's what I did. I said, I'm going to leave my 27 to the n alone. And then I can say, I know that this is -1/3 to the 3n power times -1/3 squared. Well, the -1/3 squared I'll leave there. The -1/3 to the 3n is the same thing as -1/3 cubed. Well, -1/3 cubed is -1/27. And then you say, well, yeah, but it was to the 3n power, John. I'm still leaving it to the. Why did I do that? I wanted to get the same power with the first term so I could combine those two. Now, this -1/3 squared can come out in front of your summation. You say, well, you have 1/9 times the sum. Now, you would have 27 times the -1/27 all to the n power, or that's just -1 to the n power. So now what do I know about that? And again, this confuses some people because they think, well, that surely converges. No, it doesn't. The reason it diverges is because the test for divergence, the limit as n approaches infinity of the general term, it doesn't go to 0. It's constantly either -1 or 1, -1 or 1. Since it doesn't go to 0, that series diverges, which means I cannot include 17 over 3 in my interval of convergence. Now, when I test 19 over 3, it's similar. Of course, when I plug in a 19 over 3, you have 19 over 3 minus 18 over 3, which gives me a +1/3 to the 3n plus 2 power. I go ahead and I break apart the plus 2 as 1/3 squared, bring out the 1/9 in front. And then you'd have 1/3 cubed raised to the n. 1/3 cubed is 1/27. 1/27 times 27 gives me 27 over 27 to the n power, which clearly is just 1 to the n. So that's the summation of 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. That's going to diverge off to infinity. And again, you can use the test for divergence to show that it diverges. Since the limit as n approaches infinity, the general term doesn't go to 0, it diverges. Long story short, you can't include either of your interval of convergence endpoints, and you just say it converges only if x is between 17/3 and 19/3. The last problem in this section, number 8 here, and sadly, it's a short problem too. So not only is the last problem, but it's a short one. Bummer. We have the series n plus 3 factorial times x plus 10 raised to the nth power. So you say, okay, ratio test, a sub n plus 1. All right, if I plug an n plus 1 in for that n, that's going to give me n plus 1 plus 3 for n plus 4 factorial times x plus 10 to the n plus 1 power. Divide that by a sub n, and you'll see, well, n plus 4 factorial just means n plus 4 times n plus 3 factorial. So the n plus 3 cancels out with most of that except for the factor of n plus 4 itself. Similarly, the x plus 10 to the nth cancels with all of these terms except for 1, and you'll have the factor of x plus 10. So now we're going to have, in our ratio test, the limit as n approaches infinity of the expression n plus 4 times x plus 10. Now remember, we're supposed to find the value of x that is going to make this converge. Well, this ratio test, as n goes to infinity, you're going to have infinity in there. And then you're thinking, how in the world can that be less than 1? There's only one way. So the only way, and please remember, there is always a way, and that's what we talked about in the notes. The way is if you let x equal whatever the center of convergence is. And you say, well, the center of convergence in this problem would be -10, because if I let x equal -10, you're multiplying every single solitary term by a power of 0. Yep, that's the only way. So you just say, if I allow x to equal -10, that's the only way this series will converge. And you got to think, how do I know that? Because if x is any value other than -10, you're going to have some number times a number going to infinity. It's never going to be less than 1. So you say the only value of x that's going to cause this to converge is -10 itself. And you say x equals -10, answer on achieve. All right, guys, hopefully this was a fun section for you. I loved this section. I'm just kind of sad that there was only 8 problems. I know you're sad about it too. All right, guys, hope that helps. Let me know if you have any questions.